So today we're going to talk about atmospheric properties, but we got to do a little review. You guys remember way back to week 1?
Yes.
When we got that periodic table of elements out and we were messing with building the molecules and all that, and we also talked about states of matter. Remember we had those big jars full of balls, okay? Does anyone remember, raise your hand if you can remember what one state of matter was. What was a state of matter?
Laws of motion.
No, well, we talked about laws of motion, but we're talking about states of matter. Donovan?
Plasma.
Plasma was one. Yes, that was our fourth one. Plasma was a state of matter. What was another one? Gases. We have solid, we have plasma gases. There's one more. Kenneth.
Liquid.
Liquids. Okay, so we have solids, liquids, gases, and plasma. There's some things we need to know about. Is this table a solid?
Yes.
Okay. All right, so it has a definite size. Okay. What about a definite shape?
Yes.
Yes. Okay. So solids have definite sizes and definite shapes. Okay. Now, liquid here, guys. I've got liquid in this. If you Takaya says it could change shape. How could I change the shape of this water?
Because if you say you put it in that cylinder,
Okay.
it would change shape to a cylinder.
That's exactly right. Okay. Liquids have a definite size. They're measurable, but they don't have a definite shape. It takes the shape of whatever object I put it in. If I dump it in a bucket, it's going to take a different shape. But it does have a definite size because you see how this bottle's almost full of liquid? Okay, what if I fill this cup up here? Now, can I put all of the liquid in this cup, in this bottle?
No.
Why not? What would happen?
It would overflow.
It would overflow. I can't cram all this water into this bottle because the liquid, it has a definite size. So I can't fit it all into here. What I want you to remember about liquids is they have a definite size, but they don't have a definite shape. Like Takaya said, whatever you put them in, it'll take that shape. Gases are a little different. Think about gases. Now, is there gas in this room right now?
Yes.
Air. There's air in this room. Is it filling this room?
Yes.
Okay. All right. So it's taken the shape of this room. Is there gas in that room over there?
Yes.
Okay. It's a different shape than the gas in this room, right? Because it's a different shaped room. Okay. Now size. What about size of gas? Do you think it has a definite size? This is how I like to think about gas in size. Have you guys ever seen that like brown helium cylinder that they fill up balloons with, like like a price chopper or something? You can go in or anywhere where they put that balloon on and it goes and it fills the balloon up, then it'll float, right? Okay, now, that cylinder is full of helium gas, okay, and that cylinder, guys, is about this tall, right, and this big around and that tall. So can you only fill up a balloon that's this big around and this tall? How many balloons can you fill up?
Like 10,000.
Bunches of balloons, right? Because this is what they did with that gas. They took this much gas and they crammed it down to fit in this. Because gas doesn't have a definite size, okay? So they can cram it down and fit a bunch of it into that cylinder, and then they can let it out and fill up balloons. Now, shape-wise, can you fill up a round balloon?
Yes.
What about a long balloon?
Yes.
What about a balloon shaped like an alligator? What about a balloon shaped like a heart?
Yes.
Okay, what about a square balloon?
Yes.
Okay, so does it have a definite shape? No, it will take up the shape of any container it's in. And what about size? No definite size, right? Because we can take, how much gas can we take? This, and we can cram it down into this, right? Everyone do that. This much gas, and we're cramming it into here,
We did
okay?
the same thing twice in Hollywood's room. We sat there, kept going like this.
Oh, well, or do you guys have one of these in your classroom?
Yeah.
Okay. All right, the globe shows our planet, right? Okay. Now, we've got landforms on this globe, right? You see these landforms? And we've also got bodies of water. We've got oceans, we've got lakes, we've got seas. Yes, sir, do you have something you need to add?
States and countries.
Right.
And
We've
clouds.
got, yes, we've got
And
all that
also,
on the globe.
I
Now,
think, I remember from a couple days when we came here that there's a hemisphere, a northern hemisphere, a southern hemisphere, an eastern hemisphere, and a western hemisphere.
You are correct, sir. You are correct. We talked about our states of matter that we're going to talk about today. We're talking about solids, we're talking about liquids, we're talking about gases. All right? Now, we all live in Kansas. So here we are. We found North America. We found Kansas. So we're all living here. Okay? Okay, right there. So what state of matter, if we're talking about our solids, liquids, and gases, what state of matter does our landform represent? Raise your hand if you think you know if it's a solid, a liquid, or a gas. What do you think there, Dante? A solid. So our landforms are going to represent our solids here. All right? Now, what state of matter would our oceans represent? What do you think there, Dacia? Liquids. All right? Right? They're water. They're oceans, seas, lakes. They're all water. So they represent a liquid. Now, there's one more state of matter that isn't represented on here. Donovan, what isn't represented?
Gas.
Gases. Right. So our gases are not represented on our globe, but they're around us. You guys said this room was full of air. Okay. Do you know what we call the gases that surround our planet? Mateo?
Equator.
No, that's the equator. That's an imaginary line around
I know.
Malaysia.
Air?
Okay, it is air, but we call it something else. It might be written somewhere, possibly. Kenneth?
Oxygen.
There is oxygen in our air, yes. Zoe? Gravity is a force that holds us to this earth, and we're going to talk about gravity in a minute. Okay, I'm going to give you one more hint. It's written all
Atmosphere.
over.
Atmosphere.
Okay, atmosphere. Okay, it's called our. Have you guys heard that word before?
Yes.
Yeah, you've heard atmosphere before. Okay, the atmosphere. Okay, so what I'd like you to do, let's look at the. Go ahead. We're going to write. If you look at the top of the top of page 21 here, on 1, 2, and 3, and I'm going to back this up. I want you to write solid, liquid, and gas on 1, 2, and 3, and go ahead and add a number 4 and write plasma. They're all written up here on the board just so you can see them. Solid, liquid, gas, and go ahead and add plasma to that list. It's at the very bottom. Let me put this laptop. There we go.
Hey, I can't see your pencil.
Oh, well then write it on there. Yeah, you can't see. Hurry up. Just like that. Let me ask you this. Why doesn't our atmosphere, why doesn't it just float out into space? Why do you think it stays around the Earth? What keeps it from floating off into space?
Gravity.
Gravity. Okay? So on your next line there, that's the force that holds it in place. If we didn't have gravity, it would just float away. What else would float away?
We would float.
Donovan?
We would.
We would float away. Everything would float away. Okay? So not only does gravity hold us to the planet, it holds all our chairs and our tables and our buildings and our dogs, it also holds our atmosphere, our air. It's time for our spatial awareness time. You guys have all seen a pie chart, correct? Okay. I like to call it a pizza chart. Now, if you look on your flight log there, or up here, you've got 3 different segments, right? We've got a little sliver, then we've got this wedge, and we've got this Pac-Man. Now, Nautica, how many percent is this whole pizza? The whole thing. 100%. Nautica said that our whole pizza up here is 100%. Okay? So if Christian eats half my pizza and he eats half of it, how many percent do I have left? 50%. Okay, so if half of this was 50, let's look at this big blue area. What percent, raise your hand, what percent do you think that blue area might be, Tatiana? 90? It's less than 90. Okay, Damien?
76.
76 is very close, but it's too low, and 90 is way too high. Okay? 80 is too high. So now we've got a range of 70.